thank you all for coming. I wasn't sure like how big of a speaker series this was going to be. I had no idea. So I'm glad to see all these faces. Make sure that this is on. So I really appreciate the introduction, Bob. Like he was saying, they have had sort of an eclectic experience in research and publication. And today I'll be talking about the age of fishes, the Devonian period in Arizona. I'll give you kind of a big picture view of the world. And the reason I'm doing this, the reason I think it's kind of funny that I'm doing this, is that I was born and raised in New Orleans, Louisiana. If anybody's familiar with the city, it is literally like 8 feet below sea level. So I think it's kind of appropriate that I'll be talking to you about a time where most of Arizona was also more than at least 8 feet below sea level, if not more. Seeing as this is the first talk in this series, I thought it would behoove me to talk about how we talk about geologic time, how we talk about the time scale in particular, since we're talking about the Devonian period. So I have sort of a graphic here giving you an idea about the different slices of geologic time, with eons being the longest, being from 500 million years long to more than 1 billion years long, and then eras, periods, which we're going to be interested in today, epochs, which we'll very briefly touch on, and then ages, which we're really not going to talk about at all. But I just thought I'd put that up there just so you guys could get an idea of the scale. So since this is the first talk, and I kind of didn't want to leave a huge gap from the beginning of the Earth to 400-ish million years ago, I figured it would make sense to talk a little bit about the different eons of Earth's history. We start off with the Hadean. So 4.6 billion years ago, the Earth forms. As you can imagine, there's no fossils for us to look at. There are no rocks for us to look at. So this is mostly sort of, what's the word I'm looking for here? Not something that we have a lot of physical evidence for, right? Like most of the other eons that we're going to talk about, we have a lot of evidence. We have lots of rocks, we have lots of fossils. The Hadean's one of those ones that we just don't. And it's mostly because the surface of the Earth was molten and getting hit by asteroids constantly. And it's not until the end of this time frame, of this eon, that the surface starts to solidify. We have water on the surface, and we have evidence for probably the first life forms. All right, then there's the Archean. The Archean, we have a lot of evidence for it. The Archean goes from about 4 billion years ago to about 2.5 billion years ago. The very good evidence for living things are all over the place. We have stromatolites and things like that made by cyanobacteria. And this is all basically in the ocean, right? There's nothing living on land. So you could imagine sort of an ocean world where everything that's alive is essentially a slime. You could call this the slime age. And the atmosphere at the time is mostly CO2, so it's not one of those eons of time that any of us are going to go back to and survive. We would die almost immediately. So it's a very alien world. It's not like the Earth is now. As we get through time, we're going to get closer and closer to a world that's more familiar. But in the Archean, definitely not going to be the place that you would want to be. All right, getting a little bit closer now through the Proterozoic. The Proterozoic starts 2.5 billion years ago, and it goes right up to the beginning of the Cambrian, 541 or so million years ago. Now, because of those cyanobacteria in the ocean, the ocean and the atmosphere becomes oxygenated. One of the side effects, I guess you'd say, one of the waste products of their metabolism is actually free oxygen, which starts to accumulate in the atmosphere, and it gets more to that sort of condition where multicellular life can live. And that's when the first complex life pops up. And also, we have a couple of intervals of time where the Earth basically freezes over. We're not going to go into any kind of detail about that. Just know that this interval of time with the with the snowball Earth, not the kind of place where you want to be either. The rest of the Proterozoic might have been okay, especially towards the end. There might have been enough oxygen to breathe. And in Arizona, this is represented, this interval of time, this eon's represented by the Vishnu Schist and the Grand Canyon supergroup. So if you go to the Grand Canyon now and you walk down, you hike down to the river, all of those rocks that you see down there are essentially somewhere in this time frame, something like 1.5 billion years old. Now, the Phanerozoic eon is the eon that we live in, and basically every talk in this series will be in this time frame. We're specifically going to be talking about the Paleozoic era. I'll go into a little bit of detail there, but just know that this is the time frame in which all complex life, everything that you're familiar with, this is about the time where these guys pop up. And we have a really good fossil and rock record of these guys. So this whole eon is very well represented, although not super well represented in Arizona, as it turns out. So here's a diagram of the Grand Canyon. Like I was saying before, the Vishnu Schist and the Grand Canyon supergroup, those are Proterozoic rocks. So those are like 1 billion, 1.5 billion years old. And then we have layers of rock representing the Cambrian period. So a period that we're not going to go into a whole lot of detail, but it's when the vast majority of animals and plants and that sort of thing that most people are familiar with, this is when their earliest representatives show up in the rock record. And at the Grand Canyon, we have a little sliver of the Devonian, which is the period that we're going to talk about. It's not super well represented, especially not in the eastern Grand Canyon. It's just sort of like Paleo Valley fills. And it's not the best fossil-wise. The other strata from the Cambrian and younger than the Devonian has a pretty good fossil record. The Devonian, not so much, sadly. There are other places in Arizona where we have a decent fossil record, and we'll get to that in a little while. So if we think about the Paleozoic then, this earliest interval of time where we have complex life and animals that people would recognize, the Cambrian's pretty well represented. The Ordovician, we have a little bit of that in the Grand Canyon and other places in Arizona, but not a lot. And then we basically have none of the Silurian. So we're missing this huge chunk of time. There's an unconformity at the Grand Canyon, if you guys have ever been out there and seen that. And in the Ordovician, at least, there's a lot of glaciation. Now, in the Devonian, there's lots of fish. And it's followed by the Carboniferous, which also has a lot of glaciation going on. So we're going to jump into the Devonian. Just to give you sort of the briefest idea about the ages, there are different named ages in the Devonian. We're not going to go into any real detail there other than to distinguish between early, middle, and late. And just as a sort of a foreshadowing, really what we have in Arizona is sort of like the late middle into the late Devonian. That's what we have represented in the rock record and fossils. So the geologic timescale is one of those things that is constantly changing and being added to through time. And starting in the 1800s, this is really when like the first geologic maps were being made, the really first comprehensive geologic maps. William Smith and folks like that were doing a lot of work in Great Britain, specifically in reference to coal beds, because coal was a big industry and geologists were needed for that sort of thing. One of the things that these early geologists and paleontologists noticed, though, was that there were fossils. They were much more interested in that than they were in figuring out, where's all the coal at? Even though they're paid by industry to look for the coal, they just so happened to find all these layers of fossils. And one of the things that they noticed was there were sequences of these strata, and they had different fossils in them. So one of the things they wanted to do was make a big, map of that, and that's what they did. In figuring out where the strata were relative to each other, they came up with the geologic timescale. Now, specifically for the Devonian, the Devonian was named and fully described in the 1840s, by Roderick Murchison and Adam Sedgwick. They had a kind of a dispute with Henry de la Beche about the placement of certain fossils, mostly quote-unquote carboniferous plant fossils. He thought it spanned through like lower into the section, covering what would then be the Devonian, and Sedgwick and Murchison disagreed. They did a lot of research. They went all over Northern Europe and into Russia, looking at the old red sandstones. So if you guys have ever been, and I haven't, but if you've ever been to Devon County in southwestern England, there's a lot of red sandstone. And this red sandstone, we also have that in North America, and it goes all the way across into Russia. Pretty fossiliferous, very distinct. So you'll often see in old records, geologic records from the 1800s, they'll call this the Old Red Sandstone Age. So people were already thinking about the distinctions between different geologic periods all the way back in the 1830s. So like I was saying, they had a debate with Henry de la Beche. They didn't agree about the designation for these various stages, as they were calling them at the time. And Sedgwick and Murchison went across Europe, looked at the rocks, looked at that relative to, say, like younger carboniferous rocks and the fossils that they had been finding there for some time, and came up with the Devonian period in 1840. This is what we think the world would have looked like during the Devonian. The map being where Arizona would roughly be. So most of the continents, and this is going to be true through pretty much all of the Devonian, most of the continents are in the southern hemisphere. So unlike today, where most of the continental mass is in the northern hemisphere, in the Devonian, it was mostly in the south. And we're below the equator, so we're south of the equator, and we're still kind of in this, what today would almost be the tropics. Then it definitely was, because the Earth, as we'll soon talk about, is actually a lot warmer back then. So a couple of places just to get you oriented. This is La Russia, or Euramerica. So North America is right here. Europe is right. North America is right there. Europe's right there. Arizona's over here on the end of a continental arc. You'll see that the depictions of this change as we go through time a little bit. But mostly we're in this sort of depositional basin over here, and then Ohio and a lot of other more, I would say, more famous Devonian deposits are in this basin over here. So there's not a lot of connection necessarily there. All these light blue areas, those are shallow oceans. So sort of the places that today you would expect to find coral reefs. We don't have a lot of that today. Sea level is just too low for that. All right. And this is Gondwana. So all of the southern continents, Australia's over here somewhere, Africa and South America, Antarctica, those guys are down there. So just to give you an idea. So as we step through time from the early Devonian to the middle Devonian, things are moving around a little bit. You'll notice that this deep seaway right here is starting to close up. That's going to have a little bit of an impact on the climate. We're not going to go too much into that, but it is something to be aware of. I'm just taking my time. I have no idea. Like when I start talking, I literally have no idea what time it is. And the continents are starting to move closer to one another. And one of the things that's going to happen later on as you get towards the Mesozoic, at the end of the Paleozoic, you have all the continents colliding with one another to form Pangaea, that supercontinent that I think most people are familiar with now. So Arizona is still sort of in that like tropics to subtropics area. We're below the equator. We're in the southern hemisphere at that time. And not a huge secret, but most of what we're going to be talking about is in the water. It is the age of fishes, after all. So here's a figure from one of Heidi Marie Johnson's publications. And basically, based on the rocks in the areas that she'd been to and other people had been to, we got a really good idea about what parts of Arizona would have been dry land and which would have been underwater. So the vast majority of of western and southern Arizona would have been in the shallow marine, like a carbonate ramp, sort of like the place that you would expect to find coral reefs today. But much more spread out, a much larger area than what we have currently. So just to get you oriented, we're going to be down here in Mesa, Payson's up over here, Jerome, Flagstaff, the eastern part of the Grand Canyon, the western part of the Grand Canyon. So as we talk about the geological formations in Arizona in the Devonian, one thing you ought to make a distinction between is whether or not we're off on this marine carbonate shelf or if we're on sort of low-lying land with streams and tidal channels and things like that. So there are two major Devonian formations in Arizona, the Temple Butte Formation being one of them, and it's probably the one that most people I think are going to be familiar with if you've been to the Grand Canyon. You might have seen this outcrop, potentially, especially if you've hiked down and actually put your hands on it. And in the eastern part of the Grand Canyon, where most people would have seen this, the Temple Butte is this sort of like purpley layer, I guess you'd say. I'm not that great with colors, but I always kind of associate this with purple, sort of a pinky purple. And as you'll see, some of the rocks that we have in Payson, so closer to us, are actually also this color. So in the Temple Butte Formation, based on the sort of conodonts that are there, these little fossil guys, these little tooth, we want to call them teeth. They're sort of like mouth parts for this tiny little fish thing that I'll show you guys a picture of in a little while. Based on those guys, they're very, very distinctive. They're index fossils. Based on that, the Temple Butte Formation is going to be middle to late Devonian. We don't have that sort of stratigraphic control, like age-wise, for other Devonian strata in Arizona, so it's really nice, the Grand Canyon. People go there all the time. People are very persistent in studying the Grand Canyon and figuring out these sorts of things. In the eastern Grand Canyon, like I said, you have sandstones and mudstones, limestones and things like that, and it's basically just Paleo Valley fill. So you'd have these rivers cutting down into the older Cambrian strata and filling in. And then in the western Grand Canyon, you have much thicker strata. So off on this carbonate shelf, as you might expect, you have all this room for sediment and things like that to build up. And that's exactly what happens. So you get sandy dolomite and limestones and things like that. And some of those limestones are actually built up by the corals and other calcareous critters that are out there. Unfortunately for us, or at least for me, there's not necessarily that much in the way of fish fossils that are great. I mean, they're out there, but they're not nearly as nice as they are in the Martin Formation. And I know I didn't put a slide in necessarily for that, but I am working on a site from the Payson area that has a lot of placoderm fish. I talk about that all the time, so I didn't really include it in this talk. I just thought there was so much else to talk about. I didn't want to necessarily bring that up. But the Martin Formation is middle to late Devonian, just based on the fish that are there. We don't have a lot of conodonts, we don't have ash layers to date, that sort of thing. So we're not exactly sure where we are stratigraphically. We just know that we're somewhere in that middle to late Devonian time frame. The area around Jerome has pretty thick beds, much like the Western Grand Canyon does. But in this case, we have a lot better fossil representation, especially for placoderm fish, which are the armored fish that I really like. And here's a photograph of the area, and this was taken by Heidi Marie Johnson in the late 90s, and I think that's Dr. Dave Elliott from NAU. So the Devonian in general, I think like most of prehistory, people are thinking about how hot or cold things would have been compared to today. So like as a baseline, the Devonian would have been considerably warmer than it is today. And the temperature gradient, this is, I think, the more important thing. The temperature gradient wouldn't be quite as extreme as it is today between the equator and the poles. So most of the world would have been in that sort of tropical zone, if you will, whereas the poles would have been more temperate, I guess. And reconstructions, as you can see, based on conodont, so these are the mouth plates, and it's this weird little, as you'd say, jawless fish. These guys have really big eyes, and for the longest time we had no idea what these mouth parts were from. Like, we knew they were from some sort of animal, and we really liked them because they're very distinctive, very characteristic, and they show up really well in the strata. So based on these, like you can do geochemical tests on these guys to figure out the temperature of the water that they lived in at the time. So tropical sea temperatures, sea surface temperatures would have been around 30 degrees Celsius or 86 degrees Fahrenheit, which is quite warm. These are the sort of temperatures that you don't have calcareous corals doing well in, and that's going to be sort of a thing that we'll talk about in a little while. The oceans are warm enough. There are other things that are going to be making up the reef ecosystems for a lot of the Devonian. So basically, warmer than we are today, mostly tropical. We're not going to go too much into land. We're not that interested in that sort of thing. We are talking about fish after all. And of course, pressing the wrong button. As a consequence of the world being warmer and the water being warmer, we had also higher sea level. And as far as we can tell, it would have been something like 620 feet to 390 feet above where sea level is currently. And that would make most of the continents have a lot of shallow marine environments. And these expansive shallow marine environments are really great for a lot of things that fossilize pretty well, like ammonoids. So some of the first really distinctive ammonoids show up in the Devonian. They're very distinctive, they're very well preserved. Things like crinoids, these sea lilies. I don't know if folks in the audience are familiar with crinoids or not. Some of these guys got to be like as tall as a 3-story house. So just imagine you're in a boat in the Devonian, paddling around, and you brush up against one of those. That would be terrifying. Also, lots of fish, and I think there's some trilobites in the picture. Trilobites are still kicking around. These guys are some of my favorite little bugs. And of course, so we got ammonites, we got trilobites, we got crinoids, we got fish, we have rugose corals and things like that we'll talk about a little bit more in just a second. So because we have all of these shallow marine environments and it's warm and you're in the photic zone, the idea is that you might expect there to be a lot of reef builders. And there are. It's just not quite like it is today. So not really going to be seeing like the brain coral and stag coral and stuff like that I think we're all familiar with today. You're more likely to have seen things like these rugose corals, these horn corals. And I don't know if John Christian, you brought some corals, right?
I have several species, yes.
Okay. So later on, when we're done with the talk and we've had sort of the Q&A, if people want to see the fossils that John Christian's brought, they're quite nice. And these are all ones that he's collected kind of in the Payson area, Camp Verde, places like that, right?
Some by Superior.
Some by Superior, okay. So generally, when we're talking about reefs, we're talking about reefs in the modern day. People are thinking about carbonate building creatures like red algae and the various corals that we have currently, like you might see in the Great Barrier Reef in Australia. So they're building up these wave-resistant structures. They're in the shallow water, and it's kind of nice if you live behind that. You have this very rich environment in which to live. So that's not exactly what's going on in the Devonian. In fact, there are points in time where mostly it's going to be microbes building the reefs, so things like stromatolites. I don't think I meant to put a picture of that in there, but maybe John has some stromatolites back there.
You mean stromatoporoids?
That too.
Yeah, no stromatolites.
Oh, that's okay. That's okay. So during the warmer intervals during the Devonian, the reefs would have been dominated by things like stromatolites, these bacterial colonies that build up layers. Today, the place that you could see those are in the Shark Bay in Western Australia, because the conditions there are so warm and it like kind of prohibitively bad for most things that would want to eat them, that they can build up these structures over time. And it's the sort of thing that you would have seen in the warmer parts of the Devonian, so the earlier and later Devonian, primarily dominated by stromatolites and other microbial colonies. And in the middle, when it starts to cool down, you're going to get corals, like the rugose corals, and stromatoporoid sponges, these sponges that make these huge, like, I guess, coral-like structures that John will show you some physical examples of later. All right, here's what everybody's really here for, right? The fish. So during the Devonian, there is a reason that it is called the Age of Fishes, and it's because there are so many different types of fish, and they do really quite well. So one of the groups of fishes are the ostracoderms, these jawless armored fish. These are holdovers from the Ordovician and Silurian. They're still kicking around. We have cladodont sharks. So you have some of the earliest representatives of the groups that my friend Ben Good in the back studies. You have some lobed fin fishes and some ray fin fishes, so modern groups of fishes that people are familiar with. And then placoderms. So this little guy right here is either a Stereolepis or Bothrialepis, is one of those very basal placoderms. These guys, I guess all of these guys over here, so these four, they have mobile jaws, whereas Pteraspis up here, this ostracoderm, does not. He basically just has a hole for a mouth, and you would have swam through whatever it is that he wanted to eat. The Devonian was probably a nightmare if you were a smaller fish, I would have to imagine. I can't picture being a smaller fish in this situation, because there are so many large things out there that would want to eat you. And this does come into sort of play when we talk about the earliest tetrapods later in the Devonian. So you would have had things like sea scorpions. They were still kicking around. These guys were really, really dominant in the Silurian especially, and these guys got pretty big, like the size of a car or bathtub. So imagine a scorpion chasing you around underwater. These other guys are all placoderms, so Titanichthyes, Dunkleosteus, and Heterosteus. These are placoderm fish. They are the armored fish. They have mobile jaws. And in the case of Dunkleosteus, probably one of the greatest bite forces in all of Earth's history. I can't remember exactly how many PSI it is that this guy was apparently capable of, but you definitely wouldn't want to get caught up by this guy, because he would have bitten you in half. Titanichthyes and Heterosteus and Dunkleosteus, all these guys are in excess of 16 feet in length, so killer whale sized. And in the case of Titanichthyes, it's even bigger than that. So I don't know about you, these two down here I don't think are as scary, because Heterosteus is most likely a planktivore. It would have been just kind of like trolling the bottom water and eating up all the little things that are down there. But Titanichthyes and Dunkleosteus both actively ate fish. And in the case of Titanichthyes, all he did was open his big old mouth that would have been more than a meter wide and just swam into things, as far as we know. So I don't know, if you swim fast enough, maybe you get away from him. I don't know. Another thing that happened in the Devonian is the spread of plants on land. But in the earliest part of the Devonian is very, very simple non-vascular plants that were starting to creep on to the edges of waterways, so streams, rivers, and things like that. And there was this thing called Prototaxides that may or may not have been a fungus. We're still kind of unsure about that, but these would have been the giants on the landscape at the time, whereas most non-vascular plants would have been about yay tall, like a centimeter tall, and right there on the edge of the water. Prototaxides would have been all over the landscape and would have been like towering. They would have been basically the tree equivalent in the earliest part of the Devonian. Did that run out of battery? No, there we go. Now, the nice thing about vascular plants, which are really starting to flourish as we go further through the Devonian, is that these guys had roots, and the roots stabilize the landscape. So around rivers and things like that, the banks of rivers would be more stable than they had been in the past. If you were in a landscape in the middle and late Devonian, walking through one of these really wet forests, you would have noticed a lot of fairly tall plants, but none of those plants would have had fruit. None of those plants would have had flowers. And the vast majority of them would not have had seeds either. The first seeding plants don't show up until pretty much the very end of the Devonian. You might have noticed, I guess this isn't the best picture, I should have made this bigger, but horsetails. Are people familiar with horsetails? So if you've ever been to like a pond or gone fishing, you've probably run into horsetails. They're not that big. Back in the Devonian, these guys would have been 20 plus feet tall. Yeah, shaking your head. And the forest would have been dominated by the very first of what we refer to as pro-gymnosperm plants, these plants that are going to be ancestral basically to true gymnosperms like pines and things like that and have seeds. Archaeopteris would have been basically the biggest tree on the scene. So these guys would have been 40, 50 feet tall. They have sort of fern-like leaves. They're not quite the needles that you expect out of a true gymnosperm today. But you know, they're going in that direction. Now, there are also bugs. So the second you have a viable environment on land, things come out of the water. So there are things to eat on land in the Devonian, and bugs are really the first group of animals making that journey onto the dry earth surface. Although, obviously, it's a little bit wet, it's fine. So things like trigonotarbids, these sort of arachnid relatives, these guys were all over the place. So if you don't like bugs, I don't think the middle and late Devonian would have been the time to go back to. Better than the Carboniferous, and I know nobody's going to be talking about the Carboniferous, so I'll just put it out there. Bugs were really big in the period after the Devonian, the Carboniferous. Oxygen levels get quite high, and bugs get quite large. So if these sort of things scare you, going back to the Devonian or Carboniferous is not the time for you. There would have been fairly large millipedes and other arthropods, things like that. And we don't really see a whole lot of their fossils here in Arizona, unfortunately, but there are other places around the world where they're very, very well represented. Another thing that happens because of plants moving onto land and bugs moving onto land, and there being all those terrifying things in the ocean, there are lots of animals making the move into rivers and lakes and ponds and things like that, and then eventually onto land. So fish do that eventually. They do that sort of starting in the middle of the Devonian, and by the end of the Devonian, we're getting the first things that we might refer to as true tetrapods, animals with 4 legs. So our ancestors are really taking that step out of the water at this point in time. So there's a cute little picture of Tiktaalik, this guy right here. And their relatives, their other lobe-finned fish relatives, started making that sort of journey onto land, into the rivers and onto land in the middle to late Devonian. So you can thank the climate and the welcoming climate, the welcoming forests and bugs of the Devonian for our ancestors making that trip. I didn't mention this before, but the Devonian ends in a mass extinction. Much like other periods of time, every good thing must come to an end. And the Devonian mass extinction is one of the big 5. So you can imagine a lot of the groups that we talked about didn't have a really good time during this interval. And it's not a like bad Tuesday afternoon like the end Cretaceous mass extinction was. It was more of a very bad 20 million years. So it's a protracted mass extinction. There's things going on that make conditions for life really, really bad. So the mass extinction at the end of the Devonian takes a while to get going, and the recovery from that extinction takes tens of millions of years. So going into the Carboniferous, lots of groups either didn't make it through the Devonian at all or had a really, really hard time getting back up to steam during the Carboniferous. So, one of the things that happens in the Devonian mass extinction over this pretty much like 20 million year period of time, there are two main events that people probably know, the Kellwasser event and the Hangenberg event. We're not going to talk about those as individual events. We're going to talk about this more as like a rolling mass extinction. So one of the things that happens is most of the reefs get wiped out. Conditions in the shallow marine environments become very, very bad, and we'll talk about why. And sad for me, all of the placoderm fish go extinct during this rolling mass extinction at the end of the Devonian. Trilobites, sea scorpions, these guys almost entirely disappear. You're only going to see a couple of groups of these guys in the Carboniferous. And coral was a lot more diverse in the middle and late Devonian than it is kind of currently. And it takes a long time for these guys to recover, and they never really get back because we lose some of the groups. So like I said, the shallow marine environments are hit the hardest. And one of the things we see in the rock record through this interval of time at the end of the Devonian are black shales. If you know anything about black shales, it's not good for the things that are living in those environments. This is an indication of mass die-off of things at the bottom of the food chain, like phytoplankton and things like that. So the question is, what caused this? So for most mass extinctions, people tend to think of the sort of things that ended like the end of the Cretaceous. You have a huge asteroid hitting the planet, and there's a really bad day, and there's a nuclear winter, and that sort of thing. That's not what happened during the Devonian. That very bad day with an asteroid hitting is the sort of thing where you're maybe going to have 1 million years of a bad time. You're going to have like 100,000 year nuclear winter sort of thing, but you can bounce back from that. Whereas what happens at the end of the Devonian, things are going extinct, boom, 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 because conditions are really, really bad. So one of the things that we know is happening between the Kellwasser event and the Hangenberg event is a spike in productivity for bacteria. So the plankton and stuff like that. And we can track that using, why am I blanking on that now? Yeah, zinc isotope. Like why can't I think of that? So it's an indicator of increased productivity. So you have something happening in shallow marine environments where things like plankton, algal blooms are happening, right? And that's not good for the other things that are living in that water. When that algal bloom dies and it's starting to be decomposed, all the oxygen gets taken out of the water. Things that need oxygen to live basically are going to asphyxiate and die. So this is happening over a very long period of time. So one of the things that's happening then, right, sort of a diagram depiction of that, you have algal blooms. There's a lot of nutrients then going into the water, right, so that cause the algal bloom. Those guys die, they sink down to the bottom. Oxygen is used to break those guys down. So you have ocean anoxia. Now, if this happens in a shallow marine environment, where are you going to go? If you're an animal that likes those environments, you're not going to go out into the deep ocean. And maybe this is one of those things that's driving certain animals to make that trip onto land. And as that's breaking down, also you have this thing called ocean euxemia. So not only is oxygen levels going down, but the water's becoming more toxic. And this is because of trees, apparently. So this latest research paper from Lee et al. In 2026 indicates that productivity of plants on land, so they're breaking down of rocks and dumping phosphorus into the ocean, is leading to the algal blooms. Those algal blooms are leading to anoxia. So, gee, thanks trees, I guess. And like I said, this wasn't something that just happened once. This is something that's happening over basically 20 million years. So if it only happened once, maybe things would have been fine. They would have recovered from that. But it's just not what happened. This was an extended period of time in which conditions are really, really bad, especially if you live in a shallow marine environment, because that's where all of the algal blooms are happening. So you probably thank trees for that, because trees are just exploding across the landscape, and they're doing a really good job of being trees and breaking down rocks, and those nutrients are going into the ocean. All right, so well, it did not take quite as long as I thought, but that's all right. So here are some of the references that I noted today, and thank you for your time and attention. If you guys have any questions, please let me know.